Now let's begin a discussion of the quantum mechanical description of the hydrogen atom. The idea behind this is we're going to fix the issues that the Bohr model had, right? Although the Bohr model was great for the hydrogen atom, there were some problems, and one of them is that we did not treat the electron as if it were a wave. So we're going to fix that problem right off the bat. When we come up with a quantum mechanical description of the hydrogen atom, we're going to use both the wave and the particle-like properties of electrons by defining the hydrogen atom as being an electron, which is going to act as a wave that is bound to a proton. Therefore, the electron will act as if it were a standing wave because it's bound to the proton. Now, that's going to have some important consequences for us here. And to see what those consequences are, we're going to take a look at an example that has nothing to do with chemistry. We're going to think about what would happen if you were to generate waves on a guitar string, right? Because similar to an electron, that is fixed on the end. So, if you just have an unplugged guitar string, it just sits flat like this. And then if you were to give the string some energy by plucking it, then you can generate a standing wave on here. So maybe you can generate a standing wave where there's a mode where you have 1/2 wavelength as you go from one end of the string to the other. If you were to pluck the string a little bit harder, giving the string more energy, then you can generate another mode, one in which you go through 2/2 wavelengths over the entire length of the string. But importantly, you cannot generate a mode in between these two because the ends are fixed. So you can't do, let's say, 1.6 wavelengths, because for that to happen, the string would have to end here, and it can't because it's fixed on this end to this point. To take this a little bit further, you can give the string even more energy by plucking it even harder, and in doing so, you can generate another mode where now you go through 3/2 wavelengths over the entire length of the string. But once again, you can't have anything in between the two because the ends are fixed. What we're able to see from this is that for a standing wave, there are some restrictions. And one of the restrictions is that you're only going to have integer numbers of wavelengths that are going to be allowed. Let's now take a look at a very crude model of the hydrogen atom to see this. So what I show here is a hydrogen atom. The center contains the nucleus, and then this red line will represent the wave function of the electron, right? So this is the electron's wave here. And let's say that we prepare the electron in the n=4 state. You would go through 4 complete cycles as you go around the nucleus, right? We have 4 peaks and 4 troughs, and you end up right back where you started as you go around the whole thing. Likewise, you could prepare the electron in an n=5 state, where you go through 5 complete wavelengths, right? You see here it's 5 peaks and 5 troughs as you go around the nucleus, and you end up exactly where you started. Importantly, you cannot prepare the electron in a state between 4 and 5. Right? If you were to try to prepare the electron in a state of 4 1/3, right, you'd be going through 4 1/3 cycles as you went around the nucleus. And as a result, the wave does not start and end at the same point. You get a mismatch here. And when you get a mismatch like this, there's going to end up being interference of the wave pattern, and it's going to cause the electron's wave function to cancel out. You just can't do this here. Only integer values are going to be possible here. That's our restriction because of the fact that the electron is bound to the nucleus. Because there are restrictions on the wavelengths of the electron, that will also restrict the energy levels. And that's how we're able to get discrete energy levels in the hydrogen atom spectrum. We can recover this result by explaining it through math and wave mechanics. We don't have to just say, well, let's just think of a model where there's energy levels, right? We can actually see why there are energy levels by looking at the wave-like properties of the electron. Now, to find what these energies are, you can set up and solve an equation called the Schrödinger equation. This equation takes the general form h psi equals E psi, and the math that's used to solve it is way beyond the scope of this course. This equation is a partial differential equation, and it requires a lot of calculus to solve the equation, and there's an entire class that you can take where you learn how to solve this equation. If that sounds interesting to you, I definitely recommend majoring in chemistry and taking the physical chemistry series, because in Chem 113B, you spend about 5 or 6 weeks learning how to solve this equation. I'm not going to do it here for that reason. But the results that you get from solving the equation are really important, and that's what we're going to talk about here, and that's what you'll need to know for Chem 1A. There are 3 main pieces of information that you can get from solving this equation. One piece of information is E, which will be the energy of the electron. Another piece of information that you can get from solving the equation is psi, which is going to be a function called the wave function. It describes the wave-like characteristics of the electron and its waveform. Additionally, from solving this equation, you'll get things called quantum numbers, which give you insight into where the electron is. And we'll talk about all of these things in more detail as we continue on. But first, we'll focus on the energy of the electron. So if you were to solve the Schrodinger equation for E, what you'd end up getting is that the energy of each level would be equal to negative 2.178 times 10 to the minus 18 joules times z squared over n squared. In this equation, n must be a whole number. It must be an integer value that we're going to call the principal quantum number. You can start at 1, 2, 3, 4, all the way up to a maximum of infinity. But nothing in between, right? No fractions, no decimals. In this equation, z refers to the number of protons that your species has. Now, when you look at this equation, what you see is that it bears a lot of similarity to the equation that we saw when we dealt with the Bohr model. Right? When we dealt with the Bohr model, you saw negative 2.18 times 10 to the minus 18 joules. You saw z squared over n squared. And so, interestingly here, the result that you get from solving the Schrodinger equation is identical to what you get from the Bohr model. But there are some really important differences that are worth mentioning here. Because in the Bohr model, that was an equation that was developed by assuming the answer. What I mean by that is, Bohr did the experiments, he found out what the wavelengths of light were, and then he drafted an equation that fit those wavelengths, right? So he already knew what the answer was, and then used that to come up with his equation. In the case of the Schrodinger equation, he started from first principles, not assuming any answers in that. And that is huge. So you're able to, from first principles, come up with a result that matches experimental results. Additionally, the Schrodinger equation treats the electron as both a particle and as a wave, and so it solves one of those issues that we had with the Bohr model. So this is a really big deal, and Erwin Schrödinger ended up winning the Nobel Prize for coming up with this. Now, in our next video, we're going to talk about other things that you can learn from solving the Schrodinger equation when we talk about quantum numbers and orbitals.